And yeah, so how did we do the whole thing? Because now we know what we use, but we don't really know how to hack a coffee machine. So neither me nor my flatmate are electrical engineers. I did like 2 semesters in university, but like most of the people here, probably if you didn't do a topic for years, you tend to forget everything, or most of it, as you will see throughout the process that I clearly forgot a lot. And so we did what most people would do when they figure something out that they have no clue about. We just opened this thing. So we took out all the screws that were there, literally all the screws initially that were like from the casing. So we took all sides out, even though we were only interested on this side. And there were a couple of things here that were of interest for us, and they were all in that corner. So the whole machine can be controlled. It has a major power switch on the back, but all the other controls are on the right side of the coffee machine and our buttons. So we have the buttons here, and then we have a microcontroller that does the actual work. And we have this interesting cable that connects the two. And it was interesting because it was an actual cable. They weren't soldered together or something. It was like a pretty big cable that we could just unplug. So we did that, and we just took out the whole thing. And this is what we ended up with. So this is the actual control panel of the buttons. And it allows you to basically have 8 pins down there. That's where the cable plugged in. And then you have 7 LEDs that are, on the one hand, used to show state, but they also used for error messages, etc. And then you have those 6 buttons. So the bottom right one is the important one. That's power. The top right one is espresso, and the right one in the middle is a normal coffee. The left ones are for milk coffees, etc. So we didn't focus on them initially. And this is the interesting cable. I unfortunately didn't have a picture of the original setup, so this is actually the picture of the final setup. That's why we have nice tape around it. But basically what we did is we took one side of the cable and we just jammed in a bunch of jumper wires so we could connect that to the Tesla or later into a breadboard. And then we sat down and thought about what do we actually know about this board. So we have 8 cables or 8 pins that we want to control. We have 6 switches and we have 7 LEDs. Now the idea that we had was, well, we have a cable, so if we can connect this to the Tesla and we can figure out what protocol is being spoken between this control plate and the microprocessor, we can spoof this and then just let the Tesla send this protocol. So basically what our idea was is that we have power going in from one pin, and then we have at least 3 pins that must represent the buttons, because say we have 6 buttons, we could use like a binary flag and just represent it with 3 pins. And then we have 3 pins to control the LEDs, but what is the 8th cable for? Because our math doesn't really add up here. But we figured let's go for the assumptions and try a naive approach. So this is the script to control the Tesla using Johnny 5. So we import the Johnny 5 library, and then we import the Tesla IO plugin. So that allows us to communicate with the Johnny 5 library and the Tesla. And then once the board is ready, we just create 7 pins. We omitted the one that we connected to 5 volts, because 3.3 volts didn't lit up the LEDs, 5 volts did. So you can see how scientifically we approach this whole thing. And then we set them to analog mode. So the idea was, can we figure out so analog mode measures the voltage on the pins, so we could see if there is a voltage difference when we press a button, for example. And then we injected them in the REPL, because Johnny 5 has a nice REPL, so when we start off the script, we can interact with that. So we just measured the values, and unfortunately, analog pins are very good and fluctuating, so we couldn't get a proper value out of this, so we had to tweak this slightly and take out this analog mode and turn it into a digital pin. So the difference is you can only set a digital pin to high or low, and you can only read high or low, so it's 1 or 0. And we did that, and we figured out, so when we just plug in power, we have the 3 of the right LEDs glowing up, so that's good. That part seems to be power. And if we turn off 3 of the pins, we can actually turn off these 3 LEDs. All the other ones didn't work. We literally wrote a binary flag that went through all combinations, but we couldn't get them on. But we knew 4 pins now. We knew 1 is power and 3 can control the LEDs. So we're getting close to our initial assumption. So what we did with the other 4 pins was we declared them as buttons. So Johnny 5 has a button class in it that allows us to really use the power of JavaScript by having event listeners on press and release. So this is where JavaScript is really cool for hardware hacking, because we can say, listen for whenever a button is pressed or when it's released. And it's just way easier than writing a loop and figuring out if the value changed. And we did this, and there was some notes that we took in the meantime, and I could go through them, but they all don't mean anything. But we were onto something, because we knew that pin 1 was power, 4 to 5 and 7, the LEDs we were able to control through pins 4 to 6. But the weird part was 7 and 8 were the only ones reacting on buttons. So whenever we pressed the bottom right ones, they were triggering 7 and 8 respectively. When we pressed the top 2 ones, they triggered 7 and 8. And if we set 1 bit to high, we would be able to trigger the other 2 as well. So we could use pin 2 and 3 to turn off the buttons left and right, but that's not what we wanted, right? We want to be able to figure out if that button was pressed, but we could just figure out if one of 3 buttons has been pressed, which meant that was pretty useless. So we had to go back to the drawing board, quite literally. So we took a picture of this for the first time, because I mean the plate is like this big, and we're like looking at it like this the whole time. So we figured maybe taking a picture is a bit more productive. So we took a picture, zoomed into it, and then used a software called fritzing that you can use to create diagrams. And we turned this into this beautiful diagram. And it looks like a mess, and it is a mess, because what we did is I zoomed into the picture, and I said, okay, I'm going to go from this pin to this pin because they might be connected. And then my flatmate used a multimeter to measure the resistance between these 2 parts. And if the resistance is 0, that means the 2 pins are connected. Our approach meant that we had to go from resistor to resistor as well. So that's why we left out all the resistors on this thing, or what we deemed were resistors. And while this looks like a mess, this was way more useful for us, because we could finally figure out that not only pin 1 was power, but pin 2 and 3 were power as well. And that was the reason why the other LEDs never lit on, because we had to put 5 volts on this pin in order to actually see that these LEDs light up. In the process of figuring this out, we burned 2 of the LEDs though. So by figuring out, hey, what if we connect 5 volts directly to this LED? That was at like 4 a.m., so we were slightly tired. So we broke 2, but in the end, all of them that were still working lit up, so that was a good approach. But the switches still showed the same problem. We knew that 1, 2, 3 are power, 4 to 6 are LEDs, so we were able to finally flick on the different LEDs. But 7 to 8 were still the only ones that react to buttons. And we can't figure out which button was pressed by just having 2 bits. Until we realized that 3 of these things aren't LEDs. Does anyone have an idea what this is? I mean, it's written there, but does anyone know what a diode is? All right, 1 person. So diodes are a few people. So diodes are similar to LEDs. They have one property, which is the current can only flow into one direction and the other direction is blocked. So an LED does that and light up, but a diode will just control the current going only in one direction. So we dropped the LEDs from the diagram and we added the 3 diodes, and suddenly stuff made more sense because we could follow the power and we could see where it went. And this was super useful because we finally figured out that there was a mapping, and the mapping was that switch 1 was connected between P3 and P7, switch 2 was P3 to P8, and you see that all of them are connected ultimately to 7 or 8. So that finally explained why we could only listen to the 2. It gave us the problem though that all of these switches were dependent on the input as well. and that meant we couldn't fake the protocol. We couldn't just send in high, low, to tell it what button was pressed. But we had a useful thing at home that we bought kind of in, luckily right before this hack, and those were relays. So relays are digital switches, like electronic switches that you can use, for example, a microcontroller like the Tesla to flick them rather than having to press them. So what we did is we wired the cable from the coffee machine into a breadboard, and then from there we reconstructed the same setup that we had here, just with the relays instead. So we only had 4 relays, so we decided to map only the 3 right buttons and left out the left 3. And we also wired up these these 3 LEDs to show up which status it is in, so that we know whether the coffee machine is heating right now, etc. So this was the initial wire up. We had to be very careful to not touch the hot coffee machine while testing this, even though my flatmate, I think, brewed himself twice. And then we scripted a small manual script to control this. And basically what we did is we leveraged the fact that there's also a relay class. We connected it. We said on which port we're connected to. So we connected to normally open, which means by default the switch is open. And then we just closed them immediately and injected the whole thing into the REPL so that we can control it. And now I hope the video works. So we ran Grande open at like 5 a.m. We started, I think, at 8 p.m. And it started running water. It's a bit hard to see. We didn't put coffee in it because we weren't sure yet if it works, and we didn't want to waste coffee. And once you trigger Grande close, it's gonna close again. All right, cool. So once we were done with that, we just locked up the whole thing, closed it again, properly put the sides back on, and used the fact that now that we removed the buttons, we had some holes there, so we just wired the cable through it, put a button on it, that's the Johnny 5 logo, and then wired the whole stuff on top, so that in theory we could even unplug the cables here now and plug back in the control plate, and we could use the coffee machine as intended without having broken it because we didn't solder anything. But we still don't have an IoT coffee machine, right? We were able to control this with JavaScript, but we aren't able to have something that's connected to the internet yet. And this is where my favorite status code comes in, 418, I'm a teapot. I don't know if you heard of this before. This is a suggested HTTP status code. It's not an official one, but some people use it. So if you go to google.com/teapot, it actually returns that HTTP status code. And it was suggested in the IETF RFC 2324, which is the HTC PCP, or in other words, it's the Hypertext Coffee Pot Control Protocol, which was suggested on April 1st, 1998. And this gives you an idea why we actually hacked our coffee machine last weekend, because we're approaching April 1st. And we figured it's a good point to implement this protocol. So we took this protocol actually and implemented it, or parts of it, but I first want to give you an overview of it. So it's based on top of HTTP, so you can use get and post like you're used to. You can also use the new method brew. It's not limited to the coffee protocol though, just in case you want to derive a beer brewing protocol, the RFC suggests you could use the same method. It suggests you use the safe header to recommend whether you can do the same operation again. So you can use this with conditionals as well, like if user is awake, you can't brew another coffee. And it adds a new accept additions header, so you can add milk or syrup or alcohol to your coffee. It suggests the HTTP status code 418 in case you try to talk to a teapot rather than a coffee pot with your instructions. And obviously we need to be able to address them, so it defines a URI scheme as well, and many more things. This is actually the definition of the accept additions header field. So we have milk type, syrup type, sweetener type, spice type, and alcohol type. Sweetener and spice type are not defined as what it's limited to. That's probably great for Starbucks, so they can still use this if they want to do pumpkin spice lattes. But yeah, that's basically what they recommend. This is the coffee URI scheme, and I'm happy that the screen is so big because my favorite part is this. So that's the German one, and you can see it starts with like in %4b. The reason I cut it actually out as written below is that they're internationalized, and it insists on that you use a capital K for Kaffee if you're using the German protocol. So you need to escape that by using %4b. And then we have a pod integer, and you can add additions to it. The great thing is it's alive. We actually have something working. And I'm going to do a demo, so I'm going to switch to my lovely coffee machine here. I couldn't bring my actual coffee machine because my flatmate would have been really mad, especially if I wouldn't have gotten this talk in. So I brought this coffee machine here. It's a fake coffee machine. It's basically a bunch of LEDs that simulate the 3 buttons that we would press, so you can see that the fake buttons are pressed. And then we have the script here, and we have the script running already. It's basically an HTTP server, so there's nothing hardware specific in this script. I'm using local tunnel to create an address that we can externally access. And basically, once we have that all set up, we set up the coffee machine, and when that is ready, we can use it. And then we just handle the request. So you can see we check if the coffee machine is actually a teapot, just in case. We have get methods that respond with the appropriate message coffee pot content type, which is one that is suggested in the protocol. We also have post and brew. I don't think the HTTP from Node supports brew, but I didn't try that yet. We set the headers. And yeah, we check for all the stuff like the correct content type. We check for the accept additions. Unfortunately, our coffee machine doesn't support any additions yet, but it will come. And yeah, so let's do a quick demo. I'm gonna make this a bit bigger. So I have my authorization here. It talks about security in the RFC, but I wasn't really sure they weren't really specific what the best authorization is, so I just have I created my own header. And then we specify the content type. So I'm gonna do a get actually to pod 0. So that should tell us if the internet isn't too slow. Like local tunnel is sometimes a bit slow. There we go. Currently the coffee machine is on, that's great. Now I had to improvise with the URI scheme a bit because it doesn't suggest, it's a coffee pot that supports multiple versions of coffees, which in 1998 wasn't really common. So I extended the thing a bit. So we can order an espresso, and now you should look at the LEDs. So I'm gonna do a post request to the LEDs. I'm gonna specify start. And there we go, the LED lit up. And the same for grande. We have the problem that right now we aren't able to measure whether the status is the right one, like whether it's currently brewing a coffee or not. We could figure this out by checking what the value on the LEDs are on the respective ones that we have on the original board. But the problem there is that we would literally, the current solution that we could only come up with is having a photo sensor measure whether literally the LED is on, because we don't share a common ground between the Tesla and the coffee machine, so we can't measure the values. If you want to know more about that, we can talk about that later over coffee. And yeah, so we can also turn this whole thing off. So that should trigger the other one. Boom. So that all worked. Let's quickly look at the actual coffee code. So what we do is similar to the manual script, we just initialize the different relays that we're connected to, and then we have a press power method which just checks if it's on, which currently is just a fake because I know it's it takes 20 seconds roughly to heat up. So I'm waiting for 21 seconds until it's on. And then we have a switch method, and all of them call this press button method, which in order to simulate a button press, we just open the relay, wait for 500 milliseconds, and then close it again. The reason for that is if we would just keep it open, it would just continue running until we close it again. But if we only press it shortly, it starts brewing only the amount that we need. So for an espresso, it would only brew that much rather than us having to figure out how many seconds it takes to brew a coffee. We let that be done by the coffee machine itself. And that's all, that's literally all the code that we needed. So let me switch back to my slides. All right, so what did we actually learn during this hack? First of all, reverse engineering is a lot of fun. Trying to figure this out, it's way too addicting. I think we started at 7 or 8 p.m. on Friday, and we stayed up until 6 a.m. or something until we finally had coffee, which was useful at that time because like we totally didn't want to go to sleep. But it was really a lot of fun because reverse engineering an API or something is already interesting, but reverse engineering something where you have even less of a clue, that's even better. It can be very frustrating though, because you can't just, like it's harder to reverse engineer hardware than it is to reverse engineer software. Especially because it's easier to break things, and if you're doing this in the middle of the night and you're burning something, you might not be able to get replacement parts. JavaScript and hardware work great, so this was the first time I actually did a hack with any of like the different options that we had there. I had them lying around, but I never had a good use case for it, and I think this was a really good use case. The Tesla 2 is great, like it's so much fun to work with it. It has a great CLI that you can spin up, you can easily configure the Tesla, you can run scripts on it, you can port them on it. It works really well. And Johnny 5 is super useful because it allows you to do this cross-hardware compatibility so that you can move this over to a different platform later if you want to use a different microcontroller. So what's next? We need to programmatically determine the state of the coffee machine, which, as I mentioned before, is a bit tricky right now. We need to add more relays so we can finally like add milk to our coffee. We need an Alexa integration, so we have the API now, but I figured that I finished that on Wednesday or something. I didn't have time to finish up the rest of the integration, so we need an Alexa integration, or at least an if this then that handler, and probably a Twilio integration so I can text when I'm walking home to brew me a coffee. And then if you have any suggestions, I'm more than open to hear any of your suggestions. If you have any real cool idea, like we definitely need an Irish coffee option, so we need to figure out some way how we can pour whiskey into it, since the accept editions header suggests already that whiskey is an option. And yeah, with that, thanks everyone. My name is Dominik. If I not hack coffee machines, I work as a developer evangelist for Twilio. And if you have any questions, you can grab me later for a coffee, beer, or shoot me a message. Thanks. I think we have like a minute left or something. There's a question, yeah? Yes. So right. That's exactly, that's like V4. We first need to be able to brew all this stuff. Right now the agreement that we have is whoever takes a coffee puts a new cup underneath it and puts a new, because it's an espresso, so you need to put this thing in it. So you need to put that in and put the cup back onto it. But you can do that in the evening or whenever you took the last coffee and it's ready, so that when you wake up or when you really feel like a coffee but you don't feel like making a coffee, you don't have to worry about that anymore. Any other questions? All right, thanks for your attention. Also, if you want to see the hardware, you can drop by now or later or something. I can show you the stuff.
Yeah.